Lab 2, Motion of a Falling Object, Richard Morin. Introduction Instructions. The instructions for this lab were to observe the motion of an object that dropped from rest and falls somewhat slowly straight down. The goals were to video the motion and analyze it in the tracker program, to make two computational models for the motion, one including drag and one not including drag, and then finally to compare the results. For my experiment, I used a flat 1/4 piece of copy paper as my falling object. The purpose of this lab was to evaluate the motion of a falling object, specifically through the processes of physical experimentation and computational evaluation, both in regards to drag and negligible drag. Overall, this relates to a larger purpose of understanding the physics principles behind the concept of freefall motion, in which the force of gravity is constant and always directed downwards. Through this lab, it was determined that the experiment and coding models all produced a decreasing position over time. And additionally, by the end of the evaluated time frame, the positions were that the experiment was greater than the gravity and drag model, which was greater than the gravity only model in relation to y. The models and principles used in this lab were Newton's second law being F equals ma, the position update formula, the velocity update formula, that F net is equal to a vector of the forces in x, the forces in y, and the forces in z, the force of drag equation, and from the force of drag equation, the value of b. Newton's second law is used to evaluate the forces acting upon the piece of paper as it falls, making it applicable to this lab. Additionally, the velocity update formula is also applicable to this lab as it is used to find the velocity of the piece of paper at any given time step. This velocity update formula is then used in the position update formula, which uses the velocity from the velocity update formula to find the position of the piece of paper at any given time step. The system of this lab was the following piece of paper, and the surroundings was every other object within the frame of the video, including those such as the calibration measuring tape. The initial conditions of this lab were 1. That the notebook is dropped from rest, indicating initial velocity of the zero vector, meter per second. 2. That there is a force of gravity constantly directed downward. 3. That the notebook is dropped from a set height. And 4. The notebook is known to fall to a final height of the zero vector meters. Here's my video. Using Tracker, the following graph was created. It can be seen that the y position of the paper generally decreased in a nonlinear trend until it reached the ground. Seen here is the computational aspect of this lab, specifically being my gravity-only based model. The initial conditions included that the mass was 0.018 kilograms, that the initial position was 0,0.984, 0 vector, and the delta t was 0.03 repeating. And the following F net, velocity, and position equations can be seen at the bottom. Using this code, the following graphs were created. As seen, position decreased quadratically, while velocity decreased in a linear manner. Seen now is the gravity and drag influence model of my coding. All initial conditions are the same as the gravity-only model, except for b, which is now 0.01176. This is found through using the equation b is equal to coefficient of drag times rho times area divided by 2. Additionally, the F net equation now accounts for the force of drag. Using this code, the following graph was created. As seen, position decreased quadratically, while velocity decreased in a linear manner. When all three datasets were applied to one graph, the following was created. Similarities and differences in data. So the similarities were that all three graphs indicate a negative velocity, as position is decreasing over time. Additionally, no set graph of position is exactly linear. The differences, however, was that by the end of the evaluated time period, the position of the experiment was the only positive value. Both of the coding models had a negative position by the end of the time steps, meaning that the change in y was greater for these two as compared to the experiment. Additionally, the gravity/drag model had a less negative force and velocity than the gravity-only model. So the potential errors of this experiment are 1. That the x being the x component of velocity. The paper did not fall perfectly straight, generating an oscillating x velocity which may have contributed to slightly different values. And 2. Towards the end of the flight, the paper twisted in air, making an inconsistent force of drag due to the changing area of the piece of paper. This could have also influenced the position values. So in relation to this what does it mean question, neither of my two models predicted a terminal velocity since there's no point where the velocity leveled out and ceases to decrease. This would be characteristic of the terminal velocity. Reaching terminal velocity means that the net force is 0, indicating a constant velocity. And in relation to this what-if question, the terminal velocity would be the same whether the object was thrown or dropped. According to computer models, an equilibrium and velocity will be reached at the same point whether the object was thrown or dropped. So in conclusion, the experiment and coding models all produced a decreasing position over time, and by the end of the evaluated time frame, the positions were that experiment was greater than the gravity drag model, which was greater than the gravity only model. Thank you.